Okay, so now in the previous section we showed how looking at determining the action on any, we could determine the action on any vector, right? The mapping of any vector in a linear mapping by looking at the action that it has on the basis or on a basis for that space. Okay, so for example, by looking, we could take any vector here, right, and we can find out what the action is. We can learn the action on the vector by looking at each vector as a linear combination of the basis vectors, right? And then looking at, hey, the action that it takes on each of the basis vectors will tell us what kind of action it has on any vector in the domain. Okay? And so this action describes how we can get, this describes how we can get the value of the map on any vector by starting from the value of the map using the basis vectors and then extending linearly. Okay? And this section gives a convenient scheme based on matrices to use the representation given here, to use this representation to what? To compute from the representation of a vector in the domain, the representation of that vector's image in the codomain. Okay, and so that's what we're going to do in this example here. Okay, to start things off. Okay. So in this example, we have the spaces R2 and R3. And we're going to fix these bases. So we've got these two bases, B and D. Okay, obviously, this is the basis for R2. This is the basis for R3. And we're going to consider the map H from R2 to R3 that is determined by this association. Okay? So now, let's look at how we're going to compute the action. So we're going to compute the action of the map on any vector at all from the domain. In order to compute that, we're going to first represent the vector h of beta sub 1. Okay, so let's look at h of beta sub 1. So h of beta sub 1, that is going to be what? So h of beta sub 1 right here. So here's the action. Okay, so what do we get? We get this. And so let's rewrite this as a linear combination of the basis vectors here. So that's going to give us 1 times 1, 1, 1 plus negative 2, not 2, negative a half times 0, negative 2, 0 plus, well here that gives us oh, sorry. These should be 0. There we go. Actually, no, that won't work. Let's do 0. This will be and then 1 times, I think that'll do it. Will that give us 1, 1, 1? Yes, it will. And so then the representation is going to be this. So the representation with respect to D of H of beta 1 is going to equal 0, negative a half, 1 with the capital D subscript. Okay, now let's do H of beta 2. Okay, so H of beta 2, which is 1, 2, 0, let's write this as a linear combination of the basis vectors from D. So it's going to be 1 times 1, 0, 0 plus negative 1 half, oh, hold on a second. No. We want negative 1 times 1, 2, 0 Well, this will have to be 0. The last one has to be 0 because we can't have a 1 here. So that's going to be 1, 0, 1. But then this will become 0. So let's make this a 2. And I think that'll work. No, hold on a second. One, 2, 0. Oh! I always go back and check. So yeah, okay, so that's a 0, so never mind. If that was a 1, that'd be right, but I wasn't looking. I must have got mixed up. But so it's 0, negative 2, 0. There we go. So so then this is just going to be positive 1. Yeah, that'll do it. So now we have this representation. So that means the representation with respect to D of what? Of H of beta sub 2 is equal to what? 1, negative 1, 0 with respect to D. So those are the coefficient vector, right? Okay, so far so good? Okay, so now with these, now that we have these, for any member of vector V, so any member of vector V of the domain, we can compute H of V. So how do we do that? Well, watch. Watch what we do. Okay, so now, so we have H of V, okay? Let's use what we just found. So it's going to be some linear combination of the two basis vectors here, right? So that's going to be h of what? C1 times h of two zero plus C2. Oh, hold on a second. Getting ahead of myself. C1 let's just do, I don't want to confuse you guys, so let's just use the bases. Okay, the basis vectors. Okay, so h of 2, 0 plus C2 of 1, 4. Okay, there we go. And so this is going to be equal to C1 h of 2, 0 plus C2 times h of 1, 4. All right, so far so good. And we already know what h of 2, 4 and h of 1, 4, because now we can represent these. Notice that this is now going to be equal to C1. Now what is this? This is going to be what? It's going to be equal to the linear combination. Right now we're going to use the representation with respect to D. Okay, so we know that this is going to be 0 times (1, 0, 0) minus a half times 0, negative 2, 0 plus, 1 times 1, 0, 1 plus C2 times, well, 1, 4 we wrote as what? 1 times 1, 0, 0 minus, minus 1 times 0, negative 2, 0 plus 0 times 1, 0, 1. All right. Make sense? Now, guess what? Now we're going to distribute and combine like terms, meaning we're going to group the basis vectors together. Okay? So if we distribute this, what do we get? We get, this is going to be 0, but we're going to get negative 1/2 C1 times 0, negative 2, 0, plus C1 times 1, 0, 1, plus C2 times 1, 0, 0, minus C2 times 0, negative 2, 0, and then of course that's just 0. So this is what we get, right? So now we're going to group everything. So I'm going to go back up to here. I'm going to erase this. So that should be in your notes. And I'm going to erase this. And so our result is we get C2 times 1, 0, 0. Minus 1/2 C1 plus C2 times 0, -2, 0. Plus C1 times 1, 0, 1. And so thus, what do we get? Well, here are the two representations. The representation with respect to B of the vector is just C1 and C2. And the representation with respect to D of H of V is equal to what? Well, technically it'd be 0 times C1 plus C2. And then it'd be negative the quantity of 1/2 C1 plus C2. And the last one would be C1 plus 0 C2. Oops. Okay. Oh, and there, oh, hold on. D goes here. V goes there. Okay, so now think about this. In the middle of the argument, the vector v to the map represented with respect to the domain's basis B by the column vector with components C1 and C2. On the right is the value of the map on that argument h of v2, or excuse me, h of the vector v represented with respect to the codomain's basis D. The matrix on the left is the new thing, okay? We will use it to represent the map, and we will think of the above equation as representing an application of the map to the matrix. And that matrix consists of the coefficients from the vector on the right, 0, 1 from the first row, -1/2 and -1 from the second row, and 1 and 0 from the third row. That is, we make it by adjoining the vectors representing the h sub beta sub i's. Okay, so what we're going to end up with here is this. Okay, is this representation, right? So we're going to have an augmented matrix where we're going to have the representation with respect to D on the left, oops. There we go. Okay, and so that's going to bring us to our first definition, which is going to help us because now we're going to be able to represent mappings using these augmented matrices. Okay, have a great day.